Welcome to the Platform Engineering Playbook Daily News. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're covering a counterintuitive migration story that's challenging assumptions about serverless. Unkey, an API key management platform, just rebuilt their entire service from scratch, moving from Cloudflare Workers to stateful containers. The result? A six-fold performance improvement. We'll break down exactly why they made this decision and give you a framework for evaluating your own workloads.
Wait, I need to process that. A company that went all in on edge serverless, Cloudflare Workers, durable objects, the whole ecosystem, decided to rip it out and go back to containers?
Yeah, and the reasoning is fascinating from a platform engineering perspective. But before we dig into that, we've got some Kubernetes news that's actually relevant to today's theme around infrastructure observability, the Z Pages update in 1.35.
I've been curious about this one. Z pages have been around for a while, but they've always felt like an afterthought.
Right, and 1.35 changes that significantly. Let me give you the full context, because this is genuinely useful for platform engineers building internal tooling.
Start from the basics. What are Z pages?
Z pages are debug endpoints that Kubernetes control plane components expose. We're talking kube API server, controller manager, scheduler, kubelet, chproxy, all the core components. The name comes from the URL pattern, /healthz/livezz/readyz, all ending in Z. These debug variants follow the same convention, /statusz/flagz.
So they're sibling endpoints to the health checks we're already familiar with.
Exactly. They've been around since 1.32 as alpha features, but here's what 1.35 adds: structured JSON responses with proper API versioning. This is a fundamental shift in how we can interact with these endpoints programmatically.
What endpoint specifically are we talking about?
Two main ones. First, /statusc. This gives you high-level component information, version string, the exact time the component started, uptime in a human-readable format, and a list of available debug paths you can query. Second, /flagz. This exposes all the command line arguments the component was started with.
Wait, all the flags? That sounds like it could expose sensitive configuration.
Good instinct. Sensitive values are automatically redacted, so if you have a flag that contains a password or a token, you'll see the flag name, but the value will be replaced with redacted. The implementation uses a predefined list of flag patterns that are considered sensitive.
What about the legacy behavior? Can you still get plain text output?
Yes, and this is where HTTP content negotiation comes in. By default, these endpoints still return plain text for backwards compatibility, but if you want structured JSON, you explicitly request it with an accept header.
Walk me through the exact header format.
It follows the Kubernetes API pattern. You set an accept header with application/JSON, v equals v1 alpha1, g equals config.k8s.io, as equals statusz. For flagz, you'd use as equals flagz instead. The response comes back as proper typed JSON with an API version field, kind field, metadata object, and the actual data.
That's the same pattern as kubectl get with output YAML or JSON. They're treating debug endpoints as first-class API resources.
Precisely, and it enables versioned evolution. Right now, it's v1 alpha 1, but as the API stabilizes, they can ship v1 beta 1, then v1, and clients can request the specific version they support. Your tooling won't break when they add new fields or change the schema.
What does the actual JSON structure look like for flagz?
You get a flags object where each key is the flag name, without the leading dashes, and the value is what it's set to. So you might see authorization mode with a value of node, RBAC in brackets. Profiling might be true or false as a Boolean. TLS cert file would have the file path. You can pipe that straight to JQ and programmatically check specific settings.
Give me a concrete use case. How would you actually use this?
Let's say you're running compliance automation. You need to verify that RBAC is enabled across your clusters, that profiling is disabled in production, that anonymous auth is turned off. Previously, you'd have to kubectl exec into the control plane pod, grep the process args, parse the output with fragile regex. Now, hit the flagsy endpoint, get structured JSON, compare against your policy document, and alent.
Configuration drift detection becomes trivial.
Exactly. You can build a controller that periodically queries these endpoints across all your clusters, compares the current configuration against your desired state, and alerts when there's drift. No more shelling into nodes, no more parsing kubectl describe output, just structured data you can process programmatically.
What about the security model? I assume you can't just curl these endpoints from anywhere.
Standard Kubernetes RBAC. You need to authenticate, and you need authorization to access these endpoints. They're protected the same way as HealthZ, LiveZ, and ReadyZ via the System Monitoring Group. In a properly configured cluster, you'd need valid credentials and appropriate RBAC bindings.
What if anonymous auth is enabled?
Then you could access them without authentication, which is why anonymous auth should never be enabled in production. The endpoints themselves don't have additional authentication requirements beyond what the API server enforces.
What's the practical catch with all this?
Two things. First, it's an alpha feature. You need to enable feature gates component status Z and component flag Z on your control plane components. Second, the API schema might change before it goes stable, so it's great for building internal tooling now, but I wouldn't make production monitoring critically depend on the exact schema until it reaches beta.
The curl command to hit these endpoints probably isn't pretty either.
True, you need the full authentication chain, client certificate, client key, CA certificate, the full URL with the API server address. But that's just Kubernetes security doing its job. The important thing is that once you've set up that authentication, you get structured, versioned, programmatically consumable data.
There's an interesting parallel here. Kubernetes is making its infrastructure more observable and introspectable. At the same time, teams are questioning their infrastructure choices.
That's exactly the connection to our main topic. Better observability tools help you understand what your infrastructure is actually doing, and sometimes that understanding leads to decisions like Unkey made, realizing your architecture doesn't match your workload.
Let's get into the Unkey migration. Set the context for people who haven't heard of them.
Unkey is an API key management platform. Their core product is a verify endpoint. Applications send API keys, Unkey validates them, and returns metadata about the key: who owns it, what rate limits apply, what permissions it has. Their SLA is under 40 milliseconds globally. They handle rate limiting, usage analytics, key rotation, workspace management.
So they're in the hot path for their customers' applications. Every API call their customers receive goes through Unkey first.
Right, and that's the critical context for everything that follows. They're not calling APIs. They are the API that thousands of other applications depend on. Every millisecond of latency they add compounds across their customers' entire request chains. If you're building a web service and your auth takes 30 milliseconds, that's 30 milliseconds added to every single request your users make.
And they built this on Cloudflare Workers initially?
The full Cloudflare stack. Workers for compute at the edge, durable objects for stateful coordination, think distributed counters for rate limiting, Workers KV for key value storage, the Caches API for performance optimization, plus Logstreams for log aggregation, queues for async message processing, and workflows for multi-step operations. They even built a custom Go proxy called chproxy specifically to buffer analytics events before forwarding them to ClickHouse.
That's a significant commitment to the Cloudflare ecosystem. Why did they need a separate proxy for analytics?
This gets at the fundamental constraint of serverless. Serverless functions terminate immediately after the request completes. There's no persistent process. You can't batch events in memory and flush them periodically to your analytics backend. There's no periodically when your process might not exist 1 second from now. ClickHouse, like most analytics databases, doesn't perform well with high-volume individual inserts. You want to batch writes. So they needed something stateful, running somewhere to aggregate events before sending them to ClickHouse.
So they were already building stateful workarounds to deal with the stateless architecture.
That's the pattern that kept repeating. The fundamental issue that broke things for them was caching. Their Cloudflare cache, which is supposed to be the fast path, was hitting 30 milliseconds at the 99th percentile.
30 milliseconds for a cache hit? That seems high for something that's supposed to be cached.
It is, when your target is sub-10 millisecond total response time. And here's the insight from their co-founder, Andreas Thomas. In Serverless, every cache read requires a network request. There's no guaranteed persistent memory between function invocations. Think about what happens on each request. Your function spins up, makes a network call to the cache service to get the data, processes the response, sends back the answer to the client, and then might not even exist by the time the next request comes in.
Versus a container or VM that keeps running and can hold data in local memory in a persistent process.
Exactly. A container starts up, loads your hot data into memory, and keeps it there for the lifetime of the process, which could be hours or days. Thomas put it simply, 0 network requests are always faster than 1 network request. No amount of clever caching infrastructure, no CDN, no edge network could match what a stateful server does by default, keeping hot data in local memory with 0 network latency.
Okay, but isn't that the fundamental trade-off you accept with serverless? You give up state in exchange for automatic scaling and not managing infrastructure.
That's the promise. Serverless says, you don't worry about servers, we'll scale automatically, you pay for what you use. But the complexity reality Unkey experienced didn't match that promise. They found themselves using durable objects for state coordination, Logstreams for observability, queues for async processing, workflows for multi-step operations, plus multiple custom stateful services they had to build themselves. Thomas said they spent more time evaluating and integrating Cloudflare-specific SaaS products than building features their customers actually wanted.
They were solving problems the architecture created rather than solving customer problems.
His exact words, every new Cloudflare service they adopted was a workaround for a limitation in the serverless model. And there's a vendor lock-in dimension here that's worth examining. They had deep dependencies on 6+ Cloudflare-specific services. If they ever needed to move for pricing changes, feature gaps, reliability issues, whatever, they'd essentially have to rebuild their entire backend. Every service was a Cloudflare primitive with no portable equivalent.
So what did they move to?
AWS Fargate for compute and Global Accelerator for global traffic distribution. Long-lived Go processes that hold data in memory naturally. Event batching happens in the application process without external proxies. They got to delete chproxy entirely because the container just keeps running and can batch events in memory before flushing to ClickHouse.
Why Fargate specifically? Why not EKS or Lambda?
Fargate sits in a sweet spot for their workload. They didn't need Kubernetes-level orchestration. No complex service mesh, no custom operators, no stateful sets. Fargate gives you managed containers without the Kubernetes operational overhead. And Lambda would have the same statelessness problem. Every invocation is potentially a cold start with no persistent memory. The key insight here is about cold start timing. Container cold starts happen once per deployment or scale event. You deploy new code, containers start, they warm up, and they stay warm. Serverless cold starts can happen on any traffic spike if your function instances have recycled due to inactivity. For an always hot service like API key validation, you want warm pools ready to serve, not cold starts on demand.
Global Accelerator gives them the geographic distribution they had with Edge Serverless.
Right, but with a different model. With Cloudflare Workers, your code runs at every edge location, which sounds great, but means cold starts at every edge location. With Global Accelerator, traffic routes to the nearest AWS region where they have containers running. Fewer locations, but each location has warm containers with hot data in memory.
What were the actual results?
6-fold performance improvement. And here's an unexpected benefit they didn't plan for. The container architecture made self-hosting trivial. When your product is a Docker container, customers can deploy it with a single Docker run command. That opened enterprise customers who couldn't use multi-tenant SaaS for compliance or data sovereignty reasons.
The architecture decision had product implications they didn't anticipate.
Exactly. Self-hosting wasn't the migration goal, performance was. But containers made self-hosting almost free to offer, which unlocked a new customer segment. That's the kind of second-order benefit you don't plan for, but should recognize when it happens.
Before everyone listening runs back to containers for everything, this is a specific situation, right?
Very specific. Thomas himself said if you're a small startup, medium business, or even large business just calling APIs, you probably don't need to worry about any of this. Most services aren't in the critical path of thousands of other applications. Most services don't have sub-10 millisecond latency requirements.
What's the decision framework for knowing when you're in Unkey's situation?
I'd look at 5 questions. First, where are you in the request path? Are you calling APIs, or are you being called as the API? If you're calling out to third-party services, serverless is probably fine. If you're in the critical path that other applications depend on, you need to think harder. Second, what's your P99 latency target? If you can tolerate 50 to 100 milliseconds, serverless caching might be acceptable. If you need sub-10 milliseconds, you're in different territory where network latency matters. Third, how hot is your data? If you're accessing the same keys or records repeatedly within short window periods, that data wants to live in local memory. If every request accesses different data, in-memory caching doesn't help. Fourth, what's your complexity budget? Count how many vendor-specific services you're using. If you're at 6 or more services deep in one vendor's ecosystem, you should at least understand the migration cost if you ever need to move. And fifth, can you self-host if needed? Containers make that trivial. Serverless with vendor-specific services makes it nearly impossible.
How would you measure this before committing to a full migration?
I'd profile your cache hit latency versus your target. If there's a gap, understand why. Count external service calls per request. Each one is network latency you can't eliminate. Map your vendor lock-in dependencies explicitly. And if you're seriously considering it, prototype your hot path in containers and compare P99 latency head-to-head. An afternoon of benchmarking is worth more than a month of speculation.
There's an interesting connection back to the Z-Pages discussion. Kubernetes is adding structured debugging endpoints at the same time teams are making more sophisticated decisions about compute models.
The industry is maturing in both directions. Better observability for understanding what your infrastructure is actually doing, like Z-Pages, giving you structured configuration data, and clearer frameworks for deciding how to run it, understanding when serverless makes sense and when it doesn't.
What's the takeaway for someone deciding between serverless and containers today?
It's not serverless versus containers as a religious debate. Both are tools. The question is understanding when your workload crosses the line from using infrastructure to being infrastructure. Event-driven, bursty traffic where you want to scale to zero? Serverless is excellent. Background jobs, webhooks, scheduled tasks, serverless. But latency-critical hot paths with consistent load and stateful caching requirements, that's where containers and long-lived processes win.
The question isn't which is better, it's which matches your workload characteristics.
Exactly. And for Unkey, they crossed that line. They weren't just using API infrastructure, they became API infrastructure that thousands of other applications depend on. When you're in that position, every millisecond matters, and 0 network requests for cache hits will always be faster than 1 network request, no matter how good that network is.
If this breakdown helped you think through your compute model decisions, subscribe so you don't miss the next episode.
The question isn't serverless versus containers, it's knowing when your service crosses the line from calling infrastructure to being infrastructure. And when every millisecond matters, 0 network requests will always beat 1.